I'm going to discuss. So, so as I said, we model a lot of problems based on mathematical equations, sometimes using numerical approaches, not using new equations. So there can be mathematical modeling. Physical modeling is also done, where you physically, not really. So for example, if you want to, what Dr. Prince does. So if you want to know how the flow in molten material happens, you don't really want to melt solid and see it. You can just see the fluid behavior by using any fluid which resembles as close as to the molten material you want to simulate. Okay, so instead of molten steel, can you use water? As long as viscosity is not a condition which you want to monitor or anything related to viscosity, you can use it by water. Or you can use something which is viscous. You can use a liquid polymer which is viscous, and you can see the flow behavior. You don't really need to melt anything, so you don't really need to go to that temperature. So that is physical modeling. Okay, numerical modeling, we know what that is, and mathematical modeling also we know. Okay, good. So one of the models, and let me describe these things, and I'll tell you what the problem is. One of the model which first we will discuss, the name of that is JMEK, and famously known as JMEK equation, more famously known as Avrami equation. Okay, Avrami. So A for Avrami. Okay, and the other names are Johnson. So this is Johnson, this is Mehl Avrami Koglomorov equation, and a lot of times K is also removed. So in many books you will see just JMA, Johnson Mehl Avrami equation, also known as overall transformation kinetics. This model talks about precipitation in a solid. Okay, also it should work in liquid also. Okay, but there are certain assumptions, and in any model, to make it simpler, people assume a few things, and you shouldn't make it very simple by assuming wrong things. Okay, so let us say that we have, in this section, we have some material. It can be liquid, it can be solid. Okay, so we can assume liquid also. Oh, sorry, solid also. Liquid also you can assume, but in liquid will not have grains. So, and let us say this phase is alpha. Some phase. It doesn't matter what it is. Okay. Now the conditions are so that the temperature, and if you are not changing pressure, if you are changing pressure, we don't know. Something happens. You cool it or you heat it. That the thermodynamics says that this phase now should transform to some other phase. Okay. So there can be a possibility that 100% alpha will transform to some other phase. That will be a phase transformation. Okay. There can be another scenario where it transforms to beta, but not 100%. So it will stop at, let's say, 5%, and after that it will not transform. So that will be an example of precipitation. Okay. So so for example, if you are in austenite phase in steel universe, then if you cool it down, the solubility of carbon will decrease, and carbon has to separate out. In order to support that separation, you can use some elements which can take carbon. If carbon has to stay by itself, okay. So carbon, let us say, doesn't want to join hands with anyone else, and it has to remain like as it is. Then in that case, carbon, where will it be? The best position for the carbon is the voids, octahedral, tetrahedral voids in the lattice. Okay, so voids are forming as long as there are crystals. If there is no crystal, the voids will not be forming. So carbon cannot form its own. Maybe it can. In some cases, it can form graphite, and it can have its own crystal structure. Okay. But if it is not forming graphite, then it cannot remain in isolation because it cannot occupy the atomic positions unless it transforms to some other phase. So you can help separation of carbon. So this is the lower part of iron carbon diagram, where you have austenite, and then you have this, and then you have that, and so on. So gamma is austenite, alpha is ferrite. Okay. So austenite has very high solubility of carbon. So you see it goes to a very high value of carbon. But as you decrease the temperature, austenite is not stable because no phase of iron in FCC can take that much amount of carbon at lower temperature. First, second, FCC is also not stable, so it has to change to BCC. So it changes to BCC, further decrease in accommodating carbon happens. Okay, so carbon has to go out. You can facilitate this separation of carbon by giving some elements which have a tendency to form carbides. Okay, those who can take carbide, has affinity for carbon, they will readily take carbon and they will separate out. Okay, so you can add, for example, niobium, tungsten, vanadium, chromium, molybdenum, tantalum.
Yeah.
Is there anything else? So these are the elements which will be forming carbide. So if you put them, then ferrite formation is very easy because carbon will go out. Okay, very easily. Then there are others who will not take carbon. Okay, whatever happens, it's they will, at any cost, they will not take carbon. So there, the most famous alloying element is manganese. And then apart from that, what else you can have? You can have nickel.
Okay.
And some other elements. So these will not. So if you put these elements, they will not take carbon. So carbon facilitation is gone now. So they will try to stabilize FCC. Okay. So these elements will increase the size of this phase, and it can happen that it comes to room temperature where FCC iron is stable. Okay, so that is austenitic stainless steel. So, well, so that was a different story. So here the other example will be where, let us say now tungsten carbide or chromium carbide is separating out. Okay, so to begin with, in that case it will be gamma to alpha plus chromium carbide. And these carbides can have their own kinetics. It's not very simple that from austenite it is forming M23C6. It can form different stoichiometric relations, and then at the end it can arrive at M23C6. Okay, it can start with MC, M2C, M2 point something C. Okay, and then it will, at the end it will become, do you follow what I'm saying? So, okay, so this can happen. So in this case, in this particular example, all of these grains are of austenite phase, FCC, iron or steel. Okay, and whatever chromium you need is there in it. Whatever carbon you need is there in it. Everything is there. Okay, so it's your melting pot where you're cooking whatever you want to cook, and then you slowly cool it, slowly or with a different cooling rate, doesn't matter. Just don't go to martensitic formation. And then what will happen? Then these will start stabilizing. Okay, so in this case, one phase is not just transforming to another, it is transforming to two other phases. Okay, so we will not discuss that complicated situation. Let us discuss these two. Either alpha will transform completely to beta or certain percentage of beta. So how that phenomena will happen? That phenomena has to happen by the process of nucleation and growth. Okay, so the second phase has to nucleate. Okay, and where will they nucleate? If beta has to start forming now, okay, so all the condition is good, now beta has to form. Where will it form? Where is the surface?
Grain boundaries.
Grain boundaries. If grain boundaries are not there, suppose if I have single crystal, it's the same thing. Also in damage will initiate at the secondary phase interface, whatever it is, whatever is the weakest. Okay, so if you have carbides, they will break, they will form the nucleation of whatever mechanism. So if it is ductile, then void will form by breaking of the carbides or inclusions. If they are not there, then grain boundary will nucleate a void. If grain boundary is not there, then dislocation pileups on any obstacle like lomer cortical barrier or something, they will act as the sites for nucleation of voids in damage, and in this case it will be acting as the nucleation site for the second phase. Okay, so whatever place where you have more energy available, there is a tendency to provide that energy for the formation of nucleation. Okay, and that energy, if that is given, then a nucleus will form. Okay, so a new phase will start nucleating at the boundary. It doesn't mean that it will only nucleate at the boundary. Okay, you can have nucleation inside the grain also. Okay, maybe in smaller numbers, because you should know that there are usually two mechanisms of nucleation, homogeneous and heterogeneous. Both of them are possible. Rarely homogeneous nucleation is seen, but it is possible. And even if it happens inside the grain, it doesn't mean it is homogeneous nucleation. It might be happening at some barrier of dislocation, twist boundaries, and there are other high energy areas inside the grain also where nucleation can happen. Okay, so initially they will nucleate, and then once the nucleation is done, then what will happen? They will grow. So they will grow now by the process of diffusion. So chromium will be diffusing towards these nucleus. So they have found now a colony. Okay, so some Pandey colony is there. So all the Pandays will go there. Okay, or some X colony is there. So all the X will hear on their WhatsApp that naya colony bana, chalo udhar jana. So everyone will go. Okay, so chromium will go, carbon will go, and this thing will start growing, and this will be growing on the cost of the mother phase. Okay, so this is exactly like, not exactly like, but there are a lot of analogies. So like I've given you an analogy of human behavior in stress strain diagram, right? So initially all of us can take some burden and we can recover depending upon the age and environment and all. Then we sometimes cannot go back, the damage is too much, and then we get older or sick or diseased, and so we start deteriorating, and then we die. Okay. So similarly, this process is analogous to pregnancy. Okay, so initially a fetus is forming, and that fetus is exactly equal to the mother. There is no separation, there is no identification of a new organism. Initially it's just stem cells which is dividing with its own pace, with its own kinetics, and then slowly it appears to now grow. So initially there will be a nucleation when there is, this thing is in embryo phase, and then it will become a new organism in placenta, and then it will start growing at the cost of mother's digestion. Okay, so the baby is not really breathing or eating anything, all of the things are coming through the mother. Okay, so everything is coming through the matrix, and at the cost of matrix this will grow. Okay, and once it has grown to whatever amount it can grow, then the process has stopped. So 5%, if that was possible, beta has transformed, and now you have 95% alpha, 5% beta. Okay, or 95% alpha, yeah. Okay, So this is how precipitation works. Now let us look at another scenario. And here we are not bothered about phases and other things. We are bothered about continuum mechanics. Okay, so we are really looking at the mechanics of material. Okay, in this case, the driving force is coming from the cooling, delta T. Okay, so if your temperature is going down, you have a supercooling which is providing the driving force for solidification from liquid to solid or from another solid to another solid. In this case, the driving force is coming because of the stress or strain or displacement, whatever you are applying to deform it. Okay, so that's the driving force which is causing this egg-looking shape to deform, and it will deform to a maximum, and before this maximum, it will also have grains, right? And each grain locally will have a different tendency to deformation because each will have a different Smith's factor associated with the critical resolved shear stress, and therefore not the whole stress is working on each grain to have shearing, to have dislocation movement. So different amount of dislocations are moving, getting piled up, getting blocked, and then try to overcome by cross slip, and all those phenomena are happening. Each material point, now you can look at that each material point is following with the stress strain curve, and at some point there will be nucleation of what? Voids. There will be nucleation of voids, okay, if it is ductile. So in order to model the fracture of material or damage of material, there can be basically two categories. One is stress based, another is strain based. Okay, so if strain is the defining factor which can tell you that at this point the damage or fracture must initiate, that happens usually in ductile materials. In brittle fracture you don't have significant amount of strain, so you don't really take that as a criteria. Also, brittle fractures are defined on the maximum principal stress criteria. So if maximum principal stress is higher than something, then it should break. Once the damage really reaches the critical value very soon in brittle fracture, and once it reaches, then there is nothing to model. It will break, and usually metallic materials break with the speed of sound. Okay, so the liberty ship is just cracking, and if it is holding, then there are bolts and other things. Like glass, you can see that how fast the crack grows. Okay, so these voids are nucleating. Maybe you have some precipitate, and on that, so that carbide broke, and there is a separation, and that acts as a void now. Okay, or an inclusion which broke, or there is an inclusion which is hard, but it is so sharp that the stress at the tip is larger. Okay, inclusion can also act not exactly as a crack, but it can raise the stress if it has sharp ends. Okay, so now you have voids in the system, and what will happen to these voids? They will grow, and here they will not grow because of diffusion. Okay, they will grow because of the stress, and the growth has been associated in literature with hydrostatic stress, and the nucleation of these voids has been associated with deviatoric stress. Okay, so now these voids will grow, and you have a lot of voids, and one thing which you have to remember is that when growth is happening, it doesn't mean that nucleation has stopped. When the growth is happening, nucleation is also happening. Okay, so when some of these, it's just a race who has started first. Okay, so if this void has started first and it has become nucleated, so you can define it as this void has nucleated now. Now the next thing it can do is grow. Okay, so stress is continuously increasing, and there are other points where you have secondary phase particles, blockage, high energy areas. There also stress is increasing. Okay, So while this will be growing, there will be another point where a nucleus will be forming. Okay, so nucleation is happening in parallel to growth. In precipitation, also here, when these voids are growing, not all of them, because we know that in all grains, the stress conditions are not same locally. Okay, so some of the voids are growing, and they are not growing because of diffusion, they are growing because of hydrostress, because of the stress. And while these are growing, some of them are still nucleating. The next phenomena, so in this case the story is over. Nucleation, growth, done. Okay. In this case the story is not over. So now you try to visualize this as bubbles forming in some liquid. Okay. So to stabilize bubble you need surfactants, otherwise the bubble will disappear. But they are not really bubbles, so they will remain. Okay. So you have a lot of bubbles, and a lot of bubbles are growing, some of them are still forming. And then when two bubbles come very close to each other, then they will join, because the ligament between those two will act as a tensile specimen which has neck, and it will break, and then they will join. Okay. So you have two voids and they have joined and it has become one. Okay. And this can join another one, that also can happen, and simultaneously a lot of other two voids are also joining and becoming bigger, of different sizes. Okay. And so this is called coalescence. Okay, this is called coalescence of void. And there will be a time when you have a lot of voids which have joined together and they become critically long, so that the material cannot hold anymore. This now acts as a crack and it starts propagating. Okay, and it propagates in whatever direction, in the maximum shear or whatever, it propagates, and then it will break into two pieces. Okay, so while it is breaking, you had some of the voids here. Okay, I shouldn't discuss this in this much detail, because we have to discuss this topic later on also, so I don't know why I'm doing this. So when it will break, the fracture surface will have some bigger voids, smaller void, and things like that. And so you will have some roughness on the fracture surface, which is a representation of ductile fracture, which you will not see in brittle fracture. And there are different signatures of brittle fracture. If you look it from top, then you will see the broken circles, because they were voids and they were eggs and they have broken, so you are looking at them from the top and they will look like circles. Okay, and at different resolutions you will see some lines inside these circles. Okay, and that represents that it has coalesced. It has been formed by joining a lot of bubbles. Okay, so these are called dimples, and an average dimple size can tell you about the how much energy the material has consumed, because that's how it is happening. Okay, so it is related to the fracture toughness of the material, and that we'll talk separately when we discuss quantitative fractography. Okay, so for now you know that there are similarities in these two phenomena, but there is one more step of coalescence there. In this case, so what other difference is there in these two? So suppose there is a phase transformation and there is a damage process. So what other difference is there between these two phenomena? Can you tell? So in precipitation model, we start with 100% of alpha and we go to 100% of beta. Okay, an assumption is that volume is constant. Although they will have different densities, but the model which this describes does not assume any difference in density, any difference in volume because of the transformation. But we know that it will happen. Okay, so if you freeze liquid, you will have volume expansion. Okay, so that is not taken care of here. In this case also volume is expanding. because voids are taking extra volume. Okay, so it is similar to what happens in reality, but Avrami equation will not work on this situation. So you should have an equation which can define both of them with, you know, addition of the changes which can happen because of change in density. Okay, good. So Avrami defines some nucleation rate, n dot. So n dot is a nucleation rate of beta phase. So beta phase is nucleating with this rate. Okay, so at any particular point of time tau, or in particular time of d tau, how many beta phase you will have, how much beta phase you will have. So total nucleation amount will be equal to n dot into d tau, right? So that will be very simple. Okay, and now these people have to grow. Okay, so the growth amount can be written as, and now assuming spherical particles, so you can have 4 by 3 pi r cube and into something. What will be that? What? N dot. Why n dot? हाँ, पर यहाँ तो ग्रो कर रहे हैं.
Transformation rate.
And we must also multiply with the volume, right? The total volume, because nucleation rate will be dependent on total volume. Now, what do we do?
Sigma dE.
So in some time, so at this time you have tau, and from time tau you have an increment of d tau, and in that period of time you have certain amount of nucleation. Okay, right? And in this much time you will also have some growth. No, for these particles now I need to consider some other time for which these will grow, right? So unless, let us say I start from 0, I don't have any nucleation, then growth cannot happen, right? So I must take some extra time from beyond this point, right? So tau 2, let us say. So I have to start from tau plus d tau to tau 2. I have to start from tau plus d tau, and then I have to go till tau 2, because only in that period this n, which has transformed and become nucleus, will grow. Before that they will not grow, right? So, and so those are growing, these things are growing. While they are growing, there are more nucleus forming, right? So I have to multiply this with those numbers also which have nucleated in this period of time, right? So here I will have to multiply again v n dot d, and then this tau will be tau 2 minus tau plus d tau. Okay, so in this period of time whatever has nucleated, that also I have to count, because I'm not just, so you were right, I'm not just counting how much growth has happened, I'm counting how much is the total transformation. Okay, how much is the total transformation. So nucleation happened, then these have grown and some other nucleus has formed. Okay, so now what I can do is, so I have to replace this r with growth rate. How do I do it? How is r related to growth?
Yeah, well, G is equal to
R is in, yeah. You?
so growth rate is equal to dr by r.
dr by, okay, you are talking about something else. So if there is a particle and this is r, then the volume So growth can be defined in terms of volume, right?
Yes.
So if I have some growth rate, then pi r cube, right? So, well, growth rate should be proportional to the volume, or dr whole cube, right? So how? So there can be a relation. So I can put r. I can relate r with g to the power 1 by 3, right? And then I will have some time also for growth. So that replacement is done here, so that this thing is written in the form of growth rate. Okay, so G dot is suppose the growth rate of each particle which is growing. So I have nucleation rate N dot, and then I have growth rate G dot. Okay, so this G dot, and then you will have some time for which you are growing this. So that time is d tau. Okay, so some function of this. So it will have some power. Okay, and then you will have this term, and this will be your dV beta. Right? This much amount of beta volume has formed. Right? There is a problem here. The problem is that these equations do not care if a nucleation can happen in already grown area. Nowhere in writing those equations I have taken care of that something which has grown to beta already, a new beta cannot nucleate inside it. That cannot happen, and that I have not taken care of. Okay? And the second problem is that when I have two beta and when both of them join together, they cannot grow inside each other. Right? So those equations will be making a model where you will have alpha, alpha, and then you will have beta and a nucleus of alpha inside, and then you will have scenarios where beta will be growing in beta. So it will not look adjacent to it if there is any beta. Okay? So this is called extended volume. There is extra volume coming because of these abnormalities. And then Avrami corrects it. Okay? By saying that this extended volume, the extra amount must be proportional to the truly transformed volume. And then from that relation, there comes out to be an integration, and you have a final equation in the form of something. So f alpha is equal to 1 minus some constant into t to the power 4. Is it t to the power 4 or something? T to the power n.
Yes.
And this n is found, and n or k values are found by doing experiments and plotting log and taking slope and intercepts. Okay? So that is Avrami. I am not interested in teaching you how kinetics happens and how carbides happen. Okay? I am just giving you a glimpse of similarities in a precipitation process and in a damage process. Okay? So there are other conventional models which are hardcore mechanical.
सर टेम्परेचर का इफेक्ट नहीं होता सर?
What?
टेम्परेचर का इफेक्ट नहीं होता
किसमें?
सर?
इसमें temperature constant में damage?
Yes, sir.
Yeah, we are not taking temperature there. In a transformation, temperature is needed because if you don't change temperature, phase transformation cannot happen. Or otherwise you give time, right? Because they are diffusion based phenomena. So either you provide time or temperature.
सर न्यूक्लिएशन के प्रोसेस में एनर्जी प्रोवाइड हम करते हैं मतलब
हाँ, वो mechanical energy से आ रहा है. When you do tensile test, do you provide temperature for damage?
फोर्स
हाँ?
फोर्स स्ट्रेस
Force test?
स्ट्रेस प्रोवाइड करते हैं सर हम.
हाँ, तो इसमें भी stress है ना?
तो उस टाइम टेम्परेचर इंक्रीज होता है सर, उसका मतलब एलिमेंट होता है वो गर्म होता है मतलब टेंसाइल.
हाँ, एलिमेंट गर्म होता है, टेंसाइल टेस्ट का सैंपल गर्म होता है. Then you must have done it at very high strain rate. Okay, it's a relative thing, and what you are saying is correct. Temperature changes inside the material, but then again we assume something which is called quasi-static. And the tensile tests which we do normally for steels and metallic material, we do it at a very small strain rates. Okay, so strain rates are usually of the order of 10 to the power 4 per second, or even smaller than this. Okay, so at this strain, what does it mean? That so delta L by L, so that amount of delta L is achieved in 10 to the power minus 4 of seconds. Okay, so it is very slow process, and whatever temperature changes, that temperature normalizes with the environment, so it becomes isothermal process. Okay, when you hit something, a target with a bullet, then that is an adiabatic process. Okay, in that case you are not providing sufficient amount of time for the deformation to equalize with the environment. Okay, so although there is a movement in the material points, it is called static because it is very slow, and it is not really static, so that's why it is called quasi-static. Almost as if at every step. So a tensile sample elongated at both steps as if there has been no movement in the material. So every point you can take as the reference configuration. Every point you can take as t is equal to 0. Okay, so metallic materials do not show strain rate dependence for a strain rate change of the order of 1000 at least. Okay, so if you do a tensile test at 10 to the power 4 per second, and then you do a tensile test at 10 to the power minus 3 per second, you will not see any change in stress strain diagram. Nothing. 10 to the power minus 2 also you might not see. But if you go to 10, then you will see. In order to see any significant difference in the material deformation, so meaning any time dependent phenomena is shown by metallic materials for a very great change in strain rate. Okay, so when you do a Charpy test and then you touch the sample, then it will be hot. Okay, then you can touch it and you will see that it is very hot. But if you do a tensile test and you touch it and it is hot, that means you are doing it either at a very high strain rate or there is some transformation going on. There can be a phase transformation which is going on while you are doing the test. That can give heat. Okay, because mechanically you should not get any heat when you are doing any slow testing on metallic materials, and metallic materials usually whatever we do are slow. Okay, so what was I discussing? So Avrami has not taken care of those phenomena, which is impingement of two grown particles in each other and nucleation of the product phase in the parent phase. In the product phase. So product nucleating in the product, that is not taken care of, and that Avrami takes care of later on and integrates the beta volume and then finds that equation. So F alpha really is dV beta by V beta. So fraction transform. Okay, now let us look at another hardcore model, and I will not discuss how it is derived, but well, I have only 5 minutes, so I still don't know if I can do it. So this model is called Gurson Tvergaard Needleman model, GTN. Okay, and we know that we have seen that plasticity, we say that when 1 meter passes a critical value, then we have plasticity. So our yield function usually is just sigma equivalent. If sigma equivalent is greater than sigma naught, then it is plastically deforming. If it is not, then not, right? But Gurson, he changes this and he defines a new equation for plasticity, and that equation is sigma equivalent by sigma hydrostatic whole squared plus some constant and then another variable and then hyperbolic function of cos h, another constant, hydrostatic stress normalized by yield strength, and then the same constant which appeared previously, and this variable. Okay. So when this is greater than 1, then you have plasticity. This is a new yield function, not really given by Gurson, but modified by the other two guys, Tvergaard and Needleman. Okay. So that's the and he takes a nucleation rate for voids. Okay, so let me describe what it is. Sigma equivalent, you know what it is. Okay, sigma mesis is equivalent. Sigma h is hydrostatic stress. Q1 is a constant, cos h is a function, Q2 is a constant, sigma naught is yield strength, sigma h is hydrostatic stress, Q1 is also a constant. F star, I have not told you what it is. Okay, so F star is the current value whenever you are doing this calculation, the current volume value of the void volume fraction. So this, where V beta is the amount of void which has formed. Okay, that is F star. And what he's saying is that equivalent stress is not alone describing plasticity. Plasticity will happen early if you have damage, right? And that is what we see. So this must be modified by the growth component where hydrostatic stress is taken care into account. This takes care of the nucleation, because shearing helps in nucleation, this helps in growth, there are some constants, blah blah blah, and then whatever is the amount of damage in the body. So if I take a solid steel to begin with and I deform it, and after some time I have some voids in it, the stiffness of this will go down, right? And that is what is taken care of by this term. And this is how he describes his own yielding. Okay? And then he tells that there must be nucleation rate for the voids, and that is some function, and it's a function of equivalent plastic strain rate. Let me write these equations and then I'll explain all of them. So Fg is equal to 1 minus F epsilon kk T dot, and Z is equal to Fm standard deviation 2 pi 1 by 2 equivalent plastic strain minus the mean of the distribution divided by standard deviation whole square. Okay. So now let me explain. So he takes a nucleation, and they take a nucleation rate which is Fn dot. So F in his case, in their case, defines the void volume fraction, and the amount of nucleation which is happening is a Gaussian distribution into how much amount of equivalent plastic strain is developing per unit time. Okay, so that is the rate of equivalent. So this is d epsilon plastic equivalent dt. That's that. Dot represents that. This is the hydrostatic portion of the plastic strain, and then you find out the rate of that. So that is that. Okay, so growth is related to the hydrostatic or volumetric strain rate, and then you have this F, which is this, so F star, and Z here is this Gaussian distribution where you have standard deviation, another constant, and well, this is also a constant which you don't know. Standard deviation, how much that should be. Okay, and when you have all those equations, then you can find out the value of F is equal to Fn dot plus Fg dot, and then I minus 1, then you add this F and you get I, and then you do the iteration again. Did I cross the time? 51.
Yes.
Can you give me 4 minutes? Okay. So everything is okay here. Everything is okay in this model. And if last minute is there, then I'll tell you a story also, which is a conspiracy story. It's not true. Okay? It's a rumor. So what is happening here is that, in my opinion, what is happening wrong here is you can't add nucleation rate and growth. And that's why I explained you Avrami first. Okay? Because this would mean that while growth is happening, nucleation is not happening. Okay? But this model really shows a good correlation with the experiments. Although there is another problem. The problem is, to simulate damage using this model, you need to know Q1, Q2, sigma standard, mean, what else? That's it. Oh, you need to know FM. Okay, so 1, 2, 3, 4, 5. There are 5 parameters at least, if I'm not missing something. Then those you have to find out. And how do you find out? We don't know. By fitting. So you do a lot of experiments and then you put some value of this model and then fit it with the experiment and then you find it out. There have been a lot of work to find out these things experimentally, but not really very successful. Okay? So one is a practical problem that you have to find out those parameters. Another is that this doesn't look logical. Although if you should say, looking at Avrami, that you just multiply and then things should be okay. Okay? But when you multiply and then simulate, it doesn't match. It is far away from the experiment, far away from the experiment. It really doesn't work. Okay? So some theory says that the error which is happening in addition there is somehow taken care of in Gaussian distribution here. Because at the end you are fitting these parameters or tweaking these values so that it adjusts to experimental value. Your project problem is to correct this. Okay? You have to correct Gurson, Tvergaard and Needleman model. You can use Avrami. You can use any other model. Okay? So in Avrami, how it will work is that you have the extended volume dV beta E, which is equal to the growth rate, nucleation rate into some time. Okay? So the time has to be replaced with strain because there is no time here. So that time dependence has to be replaced with a strain. In this case, precipitation, you have time. With time, you have kinetics happening. In this case, as strain develops, you have transformation happening. Okay? So that you will have to do. And then there were 2 problems with Avrami also. That nucleation can happen in already grown area. That also cannot happen here. An area which is already void, you cannot grow another void. You cannot nucleate another void in it. But impingement can happen. 2 voids can grow inside each other. It doesn't make any difference. That can happen. Okay? So you have to, there are plenty of other models. Some of them only describe the growth. For example, Rice and Tracy, it describes the growth of a void. There are n number of models which you can take help, or you can use your own brain. You can take help of anything you want. You have to correct it, and you have to, at the end, you take any number. Okay? So let us say at the end you take that at strain is equal to just at the beginning of plasticity. So sigma equivalent is equal to sigma y, or if you take another function. At that point you begin with some nucleation sites, let us say 4. For 4 of these you calculate the growth, find out for your corrected model what should be the d beta e, okay, so void volume fraction, and then you calculate the same thing using Avrami and GTN and plot them and show that whether or not it is, where it is, it's going away, is it between Avrami and GTN, where it is. Okay, Avrami really you can't apply, but you have to find some correlation of time with the strain, then you change time with a strain in Avrami and then you plot it. So that will be your project. Okay? Done then, done. So the story, kitna time ho gaya? Okay. So we are done. And the conspiracy story is Gurson was a student of Rice, James Rice. Okay, and we'll know about James Rice soon. And he has so far, I have found that he has published 2 papers only 2. Okay, and the first paper which Gurson wrote about the yield function got citations more than the cumulative number of papers Rice had written so far, his PhD supervisor. तो जितना उसने लिखा था उससे ज्यादा citation उसको एक पेपर पे मिल गया. उसके बाद गर्सन गायब हो गया. So that's the rumor. I don't know. Maybe he's there. Maybe people know him. But he's gone from literature world. He's gone. He's vanished. Okay. So then there is a story to tell. कि तुम्हारा citation PhD supervisor से ज़्यादा हो जाएगा तो क्या होगा? The other story is, which is floated, that Rice wrote his paper. And it was really, Gurson was really bad in academics, and Rice wrote his first paper and then he got too many citations, then Rice threw him out. That is one story. But if Rice comes to any of the conferences, or if you go and meet him, he is really very old, right? So when you go there, you should ask him, where is Gurson?